So today we are going to design a staircase, the simplest one of all, a single flight simply supported staircase. Okay, we have the question and I have written the main information from the question. We are going to design 1 meter wide single flight RCC staircase with height 2.7 meter. Okay, this height, this number of steps will be higher obviously. It's just a miniature diagram. You won't be having this diagram, you have to draw it yourself. Height is 2.7 meters and supported at top and bottom rises by 300 mm wide span, wide beam. Okay, so these are the beams. Okay, and the width is 300 mm, both beams. Okay, so this is a straight flight. Straight flight means there won't be any turnings or landings. It is a straight flight staircase with for 2.7 height, supported on two beams with 300 mm width. Okay, so as you all know, for this kind of stair we will be designing, or we will be assuming it as a slab, simply supported slab. Supported slab. This is a simply supported. We are assuming that this is a simply supported slab resting on these two beams. Okay, we know how we design simply supported slab. Okay, and the dimensions of simply supported slab will be, we can find the effective span from this point to this point, and we have the width. It is 1 meter. Okay, simple as that. We will be designing it as simply supported slab. Okay, so first one is effective span. How do you calculate effective span? You need to calculate the center to center distance, and it is given in page number 63 of IS 456. Okay, so center to center distance between the supports, that means from this point to this point, horizontal distance we need. Okay, so we want to calculate how much rises and how much threads are involved in this. Okay, as you know, riser is this, that is 150 mm, and this is thread 300 mm. Okay, we know that this is thread and this is riser. With this dimensions and 2.7 height, you need to calculate the number of risers and number of threads. Okay, so as you know, this will be the level of ground. Okay, this will be the level of ground, then you will be ascending from here. Okay, for example, this will be the ground level, suppose, or floor level. This height is 2.7 meter. Okay, so the number of rises you can simply calculate by dividing this 2.7 meter, right? So height is 2.7 meters, so number of rises will be equal to 2.7, which is just a simple logic. The height is 2.7 meters. We attain this height by 150 meter rises one by one. Okay, so we just want to find out how many steps we are involving. Okay, so 2.7 divided by 0.15, you will get 18 rises with 150 mm height. 18 rises. Okay, then how do you calculate the number of threads? Number of threads will be always number of rises minus 1. Okay, so for this example, 1, 2, 3, 4. It's a miniature, as I told you. Actually there are 18 rises. In this model there are only 4 rises, but there are only 1, 2, 3. This and this don't count as threads. So 1, 2, 3. So 4 minus 1. So number of threads will be always number of trices minus 1, that is 70. Okay. Now we have the number of threads. We want to get the horizontal distance. Horizontal distance means from this point or from this end to this particular end. How can you calculate that? We will calculate it by horizontal distance of stair or flight, that is, you know the dimension of thread. Single thread is 0.3 meter, and how many threads? Into 70. Okay, you will get it as 5.1 meter. Okay, so that is the horizontal distance. Okay, in this case, if this is the plan, 17 threads, this distance will be 5.1 meter. This is the plan, this is the section. Okay, side way and top view. Okay, so now we want to calculate effective span. Effective span is calculated by center to center distance between the supports, as in page number 63. Okay, so what is the support? 300 mm. So center to center distance between supports will be equal to 5.1 plus 0.3 by 2 plus 0.3 by 2, that is 5.4 meter. Okay, so 5.4 meter is the effective span. Moving on. So we have effective span as 5.4 meter. Second one, thickness of waist slab. Waist slab means this slab, this thickness. We are calculating this dimension. Okay, so this whole slab is called waist slab, and by thickness of waist slab, this is the dimension we want to calculate. Okay, as we said earlier, we are assuming this slab as simply supported slab. Okay, so we know what is the ratio to be taken with respect to L by D, which is the ratio to be taken in the page number 37. It is given as, for simply supported, it is 20. So for a slab, we will multiply it with 1.3. Okay, so we know L as 5.4 meters and D we will be calculating now. Okay, so 5.4 or millimeters, 5400 by D is equal to 20 into 1.3. D will be equal to around 207.6 mm. Okay, so obviously we will round it into next greater whole number as 210 mm. So 210 mm is the calculated thickness of waist slab. Okay, so this thickness will also be 210 mm, suppose. And now we want to calculate the effective depth. As always, effective depth will be equal to, similar to slab, we are just designing a slab and that's it. Effective depth will be equal to 210. You can say it with me, right? 210 minus clear cover of 20 for slab, clear cover is 20, and suppose we are assuming 10 mm dia bars. We will take it as 10 by 2. Okay, so we will get effective depth as 185 mm. So D is equal to 185 mm. Okay. Moving on to the main part, load calculations. Okay, so this is the tricky part regarding staircase. How do you calculate the load? Okay, so as we know, we have total load is equal to dead load plus live load. Okay, you can assume this live load, if not given in the question, as around 3 kilonewton per meter square. Okay, you can assume it's the general value. And for dead load, you will have to calculate the concrete containing in this steps and base slab. Okay, so in designing a beam or slab, there were no such difficulty. We will just multiply with the thickness and the area. We will get the dead weight, dead load. But in this case, we need to calculate this step portion also. Okay, in other words, we need to calculate additional this triangular area also. Okay, for each steps, and you need to convert it into a similar term as 3 kilonewton per mm square, something in the units of kilonewton per mm square, kilonewton per meter square. Okay, so calculation of dead load. For calculation of dead load, we will have to calculate the area of this shape. First this rectangular portion, and by second this triangular portion. Okay, then we will add these two to get the total area of this shape. Then we will multiply it with 25 kilonewton per meter cube as a weight density of concrete, as we do in every RCC structures. Then we will convert it into this unit. Okay, that's what we are going to do. So simple as that. Now first we will calculate this measurement, this slanted line dimension. How can we calculate? Simple Pythagoras theorem. Inclined length of a step is equal to, what is the length? How can you calculate? This is 300 and this is 150. 150 square plus 300 square whole root, Pythagoras theorem. Okay, you will get 335.41 millimeters. Okay, that is this dimension, 335.41 mm. You have this dimension as 210 mm, right? Then you need to calculate area of step, that is this dimension. How can you calculate that? Simply multiplying 1 by 2 into thread, we will calculate in meters, 0.3 into 0.12, so 0.15, thread and rise. Okay, that will be 0.0225 meter square, right? So you have this shaded portion area. Now we want to calculate this area. Okay, so area of wasteland or waste slab, area of inclined slab, that will be equal to 210 or 0.21 into 0.335. you will get 0.0704 meter square. Okay, and that is this area. Now you can just add these two to get the whole area. Total area is equal to 0.0225 plus 0.0704, that is 0.093 meter square shaded area. Okay, so we have the area which is 1 meter width of step of the staircase. Okay, so now you will calculate the dead load. How do you calculate the dead load? Dead load per step. Okay, per step area, that will be simply 0.093 into 1 into what? 1 is the width of step, right? 1 into 25. 25 is the weight density of concrete, RCC. Okay, so you will get it as 2.325 kilonewton per step. This is a dead load per step. You need to convert this per step value into per meter, right? Dead load per meter, that's how we calculate usually. Meter will be equal to 2.325 divided by 300. Why 300 and why not 335? Because we are taking from the top portion, right? While looking from the top portion, we are only observing 300 as thread. Okay, we are not considering it as an inclined slab, we are considering it as a normal slab. So horizontal distance should be considered. So while converting 2.325 divided by 300, that is for, we are converting it per millimeter of horizontal length of this slab. So horizontal length, for converting it into per millimeter length of horizontal length, load you will divide it to 300, and for converting it into per meter you will multiply it with 1000. Okay, so that is 7.75 kilonewton per meter square. Okay, so this is how we calculated dead load. We just calculated dead load as 7.75. Okay, I hope it's clear. We'll just calculate the shaded portion area and we'll take how much weight we'll be having for this shaded portion, that is 2.325. Then we will convert it into per meter horizontal length, that is 7.75 kilonewton per meter square horizontal. Okay, do not confuse that. So that is dead load. Live load is 3 kilonewton per meter square. So assume live load as 3 kilonewton per meter square. Total load is 7.75 plus 3, that is 10.75 kilonewton per meter square. Okay, then obviously calculate factored load. Factored load is equal to 1.5 into 10.75, that is 16.125 kilonewton per meter. So you have factored load as 16.125 kilonewton per meter. Then you will get into what? Usual step, reinforcement. Here also same as simply supported slab. For reinforcement we will need bending moment. So mu will be equal to, as it is simply supported, the usual equation WL square by 8. W will be 16.125. L will be 5.4 square divided by 8. You will get 58.78 kilonewton meter. 58.78. Okay. So we have mu, then mu limit. Mu limit is equal to, assuming FV 450. Okay. So obviously you will have to assume any type of concrete grades and steel grades. Okay. So assuming FV 450 and M20 grade concrete, 0.138 FCK BD square will be the mu limit. Substituting all the values, D is here, B is 1 meter, FCK is 20 in here, 0.138. Okay, you will get 94.4 kilonewton meter. So you will compare with this. So obviously mu is less than mu limit, so it is safe. Okay, we are on the safe side. We can carry on with this value. Okay, so carrying on, same equation for calculation of AST, the same equation as we did in slabs and single reinforced beams. Mu is equal to 0.87 Fy ASTD 1 minus AST Fy by BD FCK. Same old equation. You substitute all the values except AST. You will be getting a 2-degree quadratic equation of AST. You will get AST from the calculator as 989.9 millimeter square. So AST is 989.9 millimeter square. Okay. Then check for minimum reinforcement. Minimum AST is, for slab, as it is simply supported slab, minimum AST is 0.12% into B into D. You have D as 210 mm, D as 1 meters, so you will get it as 252 mm square. So we will check this value with AST value, 989 value. This is the minimum value. It is not less than AST minimum, so this is safe. Okay. Then the obvious step is we will calculate spacing. Spacing will be equal to 1000 A5 by AST. AST is 989.9. A5 is pi by 4, 10 square. We had assumed diameter as of reinforcement as 10 mm. Okay, then 1000. We will get spacing in here as 79.33 mm. So this value is generally considered as a low value. You can either approximate it into 75 mm, or you can redesign this with 12 mm. 12 mm diameter bar. Just replace 12 instead of 10. You do not change any our previous steps, just change here. Okay, so it's either true. You can take either of the 10 or 12 mm diameter bar. Okay, so right here I'll just take 75 mm spacing with 10 mm bar. Okay, so that is the main reinforcement. Now distribution reinforcement. So for distribution reinforcement, we have the AST value as always in slab. The distribution one-way slab distribution reinforcement is AST will be equal to 0.12 percentage, that is 0.12 divided by 100 into B into D. Okay, So 0.1, we have already calculated it as 252 mm square. Okay, and spacing will be equal to 1000 A5 by AST. That is 1000 pi by 4 into, as it is a distribution reinforcement, you will just assume it as 8 mm diameter. Okay, 8 square divided by 252. You will get it as 199 mm. We will approximate it as 190 mm spacing. Okay, so you have main reinforcement 10 mm dia bars at 75 mm center to center spacing. Distribution reinforcement as 8 mm dia bars at 190 mm center to center spacing. Okay, so these are the last points. So we are completed with the design. Now we will add this detailing of reinforcements into the diagram, and diagram is important. Okay, so we will just erase this shaded portions and all. Okay, so there will be only, we need not consider the reinforcement of beams, so that's been already designed. Okay, so you are just considering the reinforcement of this waist slab only. That's what we have designed. Okay, so this main reinforcement will be, how it will be running, spanning is from this beam to this beam. So main reinforcement will be running in this direction. Okay, so it will start like this, and there will be bottom reinforcement. It will be coming forefront and then to just a particular length like this. Okay, this is the main reinforcement, and this will be the main reinforcement. Okay, so you will mark this 10 mm at 75 mm center to center spacing is these two reinforcements. Okay, and distributed reinforcement will be provided and distribution reinforcement will be provided like cross sectionally in the spacing 190 mm. Okay, so like this. So the outer ones will be the main reinforcement, the inner ones will be the distribution reinforcement as always. Okay, so this is the general idea of how you detail the reinforcement on a single flight simply supporting staircase. Okay, thank you.